I can start now?
Yes, you can start now. You go ahead.
Okay, from scratch. Okay, everyone, good afternoon. My name is Xubao Zhang. I came from Canada. The presentation title is New Technologies of Directional Microphone for Hearing Aids. In my presentation, mic, MIC, denotes microphone. MVDR denotes minimum various distortionness response, and SPL denotes sound pressure level. I'm going to talk about three technologies which are used for hearing aids: front delay directional mic, narrow beam directional mic, and MVDR beamformer. Existing reference have briefly introduced the operation principles, performance evaluations, and field trial verification of these technologies. I worked on implementing architectures, rigorous gain equations of these relevant polar plots, the extensive experiences and advantages, disadvantage of directional mics. I made a lot of data and findings. I accomplished my research by means of latest Simulink of MATLAB R2018B and audio edition software Sound Booth SC4. The first technology is a front delay directional mic. Front delay directional mic is a variation of conventional directional mic. Subtractor exchanges the positions with the delay unit. Then subtractor is replaced with auto. We had this figure. Sorry. Okay.
Yes, good.
Okay.
Please go.
Okay, now, sorry about I made this table to show output and the signal noise ratio of omni mic, conventional directional mic, and the front delay directional mic in traffic noise and equipment noise. We calibrated noise to low-level SPL 50 dB. The data indicated that the two-directional mic and omni mic all got enough signal noise ratio to understand the noise voice. You can see this table. All the signal noise ratio is more than 10 dB. That's good to understand the noise voice. The front delay directional mic got better signal noise ratio than the omni mic in the both noises. But the conventional directional mic got better signal noise ratio than omni mic only in the traffic noise. That means front delay directional mic is better than conventional directional mic in a low-level speech, low-level SPL noise. The second technology is a narrow beam directional mic. It operated the output of bilateral conventional directional mics by a weighted sum. The priori optimized weight coefficient enabled the composite beamform to have a narrow main lobe and a flat frequency response. How narrow? This depends on the spacing between two ears. Additionally, this technology needs a two-way radio transmitter, which transmits the data of each lateral directional mic output to the contralateral directional mic to calculate the weighted sum. We have this figure you see here to compare performance between narrow beam directional mic and the conventional directional mic. A quite narrow lobe results from a tone of 800 Hertz. That's a red color one. And the extremely narrow lobe blue color results from a tone of 2K Hertz. But two high wide side lobes accompany it. We had this table here we can see to show signal noise ratio of narrow beam and conventional directional mics output. Test condition, traffic noise, and target voice both were SPL 60 dB. Spacing of ears was 16 centimeters. With azimuths of traffic noise 45 degree, 90 degree, and 135 degree. Output signal noise ratio of the conventional directional mic were 0.6, 4, and 10 dB respectively. You can see in this table, conventional directional mic. While output signal noise ratio of the narrow beam directional mic were 4.1, 8.6, and 13.5 dB respectively. The bottom data at a narrow beam directional mic. The narrow beam directional mic improved signal noise ratio by 3.5 to 4.5 dB over the conventional directional mic in the field of common voice plus traffic noise. The third technology is MVDR beamformer. We had this figure, you can see this button, to show implementing architecture of MVDR beamformer. The main beamformer is composed of the middle and bottom blocks. In left of these figures here, the main beamformer output subtracts the noise estimator output to extract the speech signal. Here is a main lobe beamformer. Its output subtract the noise estimator output. The noise estimator could estimate, Then the output, we can see this output is a speech signal. So the main main beamformer output subtract we made this table to show output and signal noise ratio of omni mic, conventional directional mic, and MVDR beamformer in 60 dB noise field. The omni mic performed signal noise ratio 1.1 dB, voice at 0 degree and 90 degree. The conventional directional mic signal noise ratio 6.5 dB at 0 degree and 1.2 dB at 90 degree. And the MVDR beamformer signal noise ratio 4.2 dB at 0 degree and 4.1 dB at 90 degree. So the range of hearable voice elements was extended. This is we want. We had this picture to show waveforms of MVDR input output and noise remover output. The surrounding noise had a power competing with the target voice. Signal noise ratio of the MVDR beamformer output was not satisfactory. You can see just 4 dB signal noise ratio. That's not big enough to listen the sound, the speech. So we have the noise remover. The sound, the algorithm is silent interval speech, interval spectral subtraction reduce the gain of speech and noise only around the silent intervals. In this picture, the blue color is speech signal, yellow color is noise signal. So the noise remover only reduce the gain around the silent intervals here and here. After processing, the remaining noise was removed, especially in the non-voice interval. Especially here, you can see noise reduced a lot, but here speech signal we don't reduce gain. Now we have conclusions. The front delay directional mic had speech enhancement 6 dB. Spectrum of its speech output was preserved. Its performance of noise reduction was better than the omni mic, but not better than the conventional direction mic. So it was suitable for use in a low or soft level noise environment. Simple combination of front delay directional mic with the conventional directional mic could achieve better speech intelligibility. The narrow beam directional mic enabled the low width of the composite beamformer to reduce from plus minus 90 degree to plus minus 60 degree, thereby effectively separates the interfering noise nearby the target voice. Compared to the conventional directional mic, It improved signal-noise ratio by about 4 dB in common practical situations. The MVDR beamformer introduced both multi-azimuth target voice and noises. It used the reverse cardioid directional mic to estimate the noises. When the main beamformer output subtracted the noise estimator output, the intruding noises were suppressed or cancelled. Such MVDR processing could detect the open multiple voice effectively and did not cause speech distortion at all. Additionally, combined with silent interval spectral subtraction, the MVDR beamformer suppressed the surrounding noises well. All the new technologies reach their expected goals. Okay, that's all for today. Thanks, everyone. Host, I'm done.